Welcome back to the class on electrical machines 2. In this lecture, we are going to discuss about the no-load and block rotor test on a three-phase induction motor. In the last class, we have developed the equivalent circuit of induction motor. That equivalent circuit is consisting of stator resistance, stator leakage reactance, magnetization reactance, rotor resistance, and rotor leakage reactance. We can do the theoretical analysis only on that equivalent circuit if you know the parameters in that equivalent circuit for given induction motor. Now, in this lecture, how we are going to calculate that parameters of a given induction motor by conducting a no-load and a block rotor test on a three-phase induction motor. This is the circuit diagram for the no-load test on a three-phase induction motor. This is the stator winding. This is the rotor. For the stator winding, we are applying a three-phase supply through the three-phase auto transformer. This is the ammeter to measure how much current is taken by the induction motor. Here we are using the 2 wattmeter method to measure how much power is taken by the induction motor. So that here we have taken 1 wattmeter. This is another wattmeter. This is the current coil. This is the pressure coil of the wattmeter. To measure how much voltage we apply to the induction motor, here we connect a 1 voltmeter. No load test. No load test is nothing but we should not apply any load on the induction motor. In this test, we have to apply the rated voltage to the stator winding of induction motor. By gradually changing the variable knob of three-phase auto transformer, you apply the rated voltage to the three-phase induction motor that we can read by means of a voltmeter. So whenever the flux is creating from the stator winding, there is a voltage will be induced in the rotor winding. The rotor also will be rotating in the same direction of a stator flux. The rotor speed is almost all equal to the speed of a stator flux. So the slip of the induction motor during the no-load test of a three-phase induction motor is very, very less. So whenever we apply the rated voltage to the three-phase induction motor, then you note down the readings of voltmeter, ammeter, and 2 wattmeters. So this is the table, serial number, voltmeter reading, ammeter reading, and wattmeter. The sum of the wattmeter readings of these 2 wattmeters is representing the power taken by the induction motor during the no-load test. VNL is nothing but the voltage applied to the induction motor during the no-load test. INL is nothing but the current taken by the induction motor during the no-load test. From the no-load test, we have 3 readings. One is voltmeter reading, ammeter reading, and wattmeter reading. This is the exact equivalent circuit of a induction motor. This is the stator resistance. This is the stator leakage reactance. This is the magnetization reactance. This is the rotor resistance referred to the stator. This is the rotor resistance along with a electrical equivalent of the mechanical power developed in an induction motor. At no load, the slip of the induction motor is very, very low. So this quantity will be higher. Nothing but this branch is consisting a high amount of the impedance that is parallel to the magnetization reactance. When a small value and a high value is parallel means the resultant impedance we are getting the small value. So the equivalent circuit of an induction motor during the no-load test becomes this one. See, this is RS, this is JXS, this is XM. This is the voltmeter reading, this is the ammeter reading. When you're seeing the circuit between these 2 terminals, the no-load reactance is nothing but the sum of the stator reactance and magnetization reactance. This is nothing but a self-reactance of a stator. From the instrument readings in a no-load test, the per phase impedance of induction motor during the no-load test, ZNL equal to VNL by INL. This is the voltmeter reading, this is the ammeter reading. No-load resistance of induction motor during the no-load test, RNL equal to the power taken by the induction motor divided by square of the current taken by the induction motor, that is the INL square. The per phase reactance of induction motor during the no-load test, XNL equal to square root of ZNL square minus RNL square. This ZNL is nothing but the no-load reactance of induction motor during the no-load test. Already we know the equivalent circuit. The reactance value during the no-load test of induction motor from this equivalent circuit, that is equal to XS plus XM. This is one important equation. Block rotor test on three-phase induction. The name itself, it is there, the block rotor test. Nothing but we are blocking the rotor. So whenever we are blocking the rotor, the induction motor will be representing as a secondary winding is short circuit. Three-phase supply is there. Three-phase auto transformer to apply the regulated voltage to the induction motor. This is the ammeter. This is the voltmeter. This is the wattmeter 1. This is wattmeter 2. In this test, you apply the voltage gradually. Make sure that the ammeter reading is equal to the rated current of an induction motor. Then you note down the readings of voltmeter, ammeter, and watt. So whenever you are blocking the rotor of induction motor, even less, if you apply the less amount of voltage, high amount of current is passing through the induction motor. That you have taken care while you are applying the voltage to the induction motor. So here the rotor is not rotating because we blocked the rotor. The voltmeter reading we have taken the VBR, nothing but the voltage applied during the block rotor test. IBR is nothing but the current taken by the induction motor during the block rotor test. WBR is nothing but the power taken by the induction motor during the block rotor test. So whenever you are blocking the rotor of induction motor, the slip of the induction motor becomes a 1. This is the exact equivalent circuit of induction motor. During the block rotor test, the slip of the induction motor becomes a 1. So RR dash by S becomes a RR dash. So one more thing is, for simplified calculation, we are assuming that stator number of turns to the rotor number of turns ratio becomes a unity. So by the time RR dash equal to RR, X2 dash is equal to X2. Now this is the equivalent circuit of induction motor during the block rotor test. The block rotor impedance equal to ZBR equal to the voltage in a block rotor test divided by the current taken by the induction motor during the block rotor test. The block rotor resistance of induction motor RBR equal to VBR by IBR square. The per phase block rotor reactance XBR equal to square root of ZBR minus RBR square. Here square is there. So we got this value. So from the readings, we know the resistance value as well as the reactance value of a induction motor during the block rotor test. Now these two values we are making equal to the real part of the impedance of the circuit and the reactive part of the impedance of the circuit. From this equivalent circuit, these two in parallel. So JXM into RR plus JX2 divided by sum of these two impedances RR plus JX2 plus XM, that is series with a stator impedance. So RS plus JXS. This is equal to RBR plus JXBR. Now here this quantity we are rationalizing. We are multiplying the numerator and denominator of this quantity with a RR minus JX2 plus XR. Now we are simplifying the numerator. The denominator, this is like a plus B into A minus B. So the denominator we can write it as a RR square plus X2 plus XM whole square. In the numerator, if we simplify means JXM into RR square plus X2 square plus X2 XM minus JRR XM. Now here we are defining the one quantity X2M, rotor self-reactance. Rotor self-reactance is defined as a magnetization reactance plus rotor reactance. So X2M equal to X2 plus XM. See here in these two terms, if we take the X2 common, we are getting X2 into X2 plus XM. In place of X2 plus XM, you can substitute the X2M. So finally, we are getting the RS plus JXS plus JXM into RR square plus X2 into X2M minus JRR XM whole divided by RR square plus X2M whole square. This is the right hand side. The left hand side of the equation becomes a RBR plus JXBR. Now we are going to equate the both real term and imaginary term on both sides of the equation. Now equating the imaginary term on both sides of the equation, XBR equal to XS plus, see here, This part is consisting a JXM. When JXM is multiplying with a real term in the bracket, it gives the imaginary term. When the JXM is multiplying with a J term in the bracket, it gives the real term. So here we are getting the XBR equal to XX plus XM into RR square plus X2 into X2M divided by RR square plus X2M whole square. This is the imaginary term of this equation. Now we are going to simplify this equation. Now XBR equal to XM into RR square by X2M plus X2 divided by RR square by X2M plus X2M. Numerator and denominator we are dividing with a X2M. RR is nothing but a per phase rotor resistance. X2M is nothing but a self reactance of a rotor, that is equal to X2 plus XM. In any induction motor, XM value is very, very higher. RR value will be very, very low. Denominator becomes a very high value. The numerator value becomes a very low value. So finally, this quantity becomes a very small value. So in the numerator and denominator, we are neglecting these two terms. So finally, we are getting the XBR equal to XX plus XM into X2 by X2M, where X2M equal to X2 plus XM. So this is equal to XS plus XM into X2 by X2 plus XM. See here, the magnetization reactance is far, far greater than the leakage reactance of a rotor winding of induction motor, which is X2. The parallel combination of small value and large value, the resultant value, we are getting the small value. So XS plus, generally in case of induction motor, when you're going to refer any element, resistance or reactance, refer to the stator or the rotor side, almost all those values are equal. So stator leakage reactance equal to rotor leakage reactance, refer to the stator, that is equal to XBR by 2. Once we got the value of stator leakage reactance XS, from the NoLoad test, we have a one relation XNL equal to XM plus XS. So the magnetization reactance equal to XNL minus XS. From the NoLoad readings, we know this quantity. Just now we know the XS value also. Then we can find out the magnetization reactance. Up to here, we can calculate the three parameters. One is XS, second one is X2, third one is magnetization reactance. How we are going to calculate the stator resistance means by conducting a volt ampere test. This is the stator winding, which is connected in a star, that we assumed that. Now for this one phase, we are going to apply the regulated DC voltage through the potential meter. This is the DC voltage. This is VDC. So from this point, you connect it to the one phase. Here this you take the A phase. Here you keep a one ammeter. Here we keep a 1 voltmeter. Apply the less amount of voltage to the one phase, note down the ammeter reading. Again increase the voltage, note down the ammeter reading. Again increase the voltage, note down the ammeter reading. In this manner, we are going to take the serial number, voltmeter reading and ammeter reading, at least 5 readings. 1, 2, 3, 4, 5. 5 readings. In each case, you note down how much is the resistance, nothing but a voltmeter reading by ammeter reading. Here we are getting the R1, R2, R3, R4, R5. In each reading we are getting. Now RDC, R1 plus, R2 plus, up to R5 divided by the 5. Nothing but this is the average value we have taken. But actually this winding will be operating at AC voltage. The resistance value also will be increased due to the skin effect. So the resistance of the winding RAC equal to 1.5 times the RDC. So this is nothing but a RS. Now we are going to calculate the one more parameter, that is the rotor resistance. To find the rotor resistance, now we are going to equate the real part of the above equation. The per phase resistance of a induction motor during the block rotor test, RBR equal to RS plus RR into XM square by RR square plus X2 square. normal design of the mission, X2 is far greater than the RR. So in the denominator, we are neglecting the value of rotor resistance. So the above equation will be reduced to the RBR equal to RS plus RR into Xm by X2 whole square. Now here the unknown parameter is RR. RR is nothing but the per phase rotor resistance. RR equal to RBR minus RS into X2 by Xm whole. In this equation, we know the RBR values from the block rotor test meter readings. RS is nothing but a stator resistance. Already we calculated this value. X2 is nothing but a rotor standstill reactance. It is also calculated. Xm is nothing but a magnetization reactance of induction motor. It is also calculated. So you can calculate the rotor resistance by using this equation. In this manner, we are going to calculate the 5 parameters of a equivalent circuit in an induction motor, that is stator resistance, stator leakage reactance, magnetization reactance, and rotor resistance, rotor standstill reactance. Thank you very much. If you have any doubt, you can ask me directly or you can ask in the comment box of my YouTube channel, so that I'm always welcome to answer all your questions.